Hey everybody! Right guys, so we're on AS Bonding Lesson 12. Can you believe this? So today we're working on dative covalent stroke coordinate bonding, and we're also doing dot and cross today. So I'm going to share my screen. Let's crack on. Let's see if I'm going to load up the YouTube video. Swing that over to there. We're also doing dot and cross today. Pop out the chat. Pop out chat. There we go. So that's all working okay. If you guys can say hello, I'll add the YouTube link to the chat just since. There we go. We're in. Right. Register's done and she isn't here. I'll then get rid of my YouTube video since I know the sound's working okay. Yeah, just hey, Hearn, good to see you. Hey, Louie. We're there. All right. I'll switch my camera to my clip cam. Doing quite well on these things at the minute. Now that I've, unfortunately, Harry, your microphone that you got me is causing me issue, although I think it's actually the splitter. I think it's my cheap splitter that I got from Lazada. Right. Harry's there. Amazing. Right. Shared screen. We're done. Okay. So we're on to dative covalent and dot and cross. 3 learning objectives today, folks. 3 learning objectives. Know dative covalent and coordinate bond and be able to spot it in reality. Number 2, be able to draw dot and cross and be able to do oxidation states. Okay, so dative covalent bonding. This is not a complicated addition to your knowledge here, guys. But it is something that's purely A-level. You don't come across dative covalent in GCSE. So this is a new concept, but it's a concept which is easy to grasp. So first of all, we need to give a definition. So definition. Now there are 2 words for this, and you may use either one, whichever one you prefer. I prefer dative covalent because it reminds me that it's a covalent bond, but you can do either. So I'll put dative covalent bond, and I will put underneath it, otherwise known as a coordinate bond. You can do either one, whichever. So a dative covalent bond, a covalent bond where both electrons in the bond come from one atom in the bond. I'll explain. I prefer the diagram than the words. So this is a standard covalent bond. So I'll do X and Y. Here's a standard covalent bond. Yeah, and we draw it as a dot and a cross, because what we're doing is the cross and dot represent that each of the electrons came from different people. This here is a covalent bond. So, and it's represented via the stick picture like this. There we go. But then a dative covalent is when both electrons have come from one of the people in the group, in the pair. So this is a dative covalent bond, and it, as the stick diagram, it's represented like this, because what this arrow says is that both electrons came from X. That's what it says, because essentially the arrow is saying where the electrons have gone to. Yeah? Okay, so now what we need to do is we need to show some examples of these. So, now Edexcel. Hey, Ange, good to see you, dude. Ange, I'll add you to the register. Oh, no. I'll add you to the register, Ange. Stop screen share. There we go. There you go, Ange, you're in. Share screen. Put that back on. There we go. Okay, so Edexcel have particular examples that they'd like you guys to know. So example number 1 from Edexcel starts off easy. So the example number 1 is the ammonium ion. Ammonium. You've got to know your complex ions. So the ammonium ion, so what we need to do is we need to explain how this has come about. So what we started off with, bullet point number 1 with ammonia. Now we know what ammonia looks like, NH3, and thanks to GCSE, we can draw a dot and cross, which looks like this. Look how beautiful my circles are today. Oh, and then I ruined it. There you go, that's not bad. So here's ammonia. And nitrogen has a lone pair. Lone pair of electrons. Now what we know is that ammonia is a base. Yeah? What that means is it can react with acids. And we know that acids are H+. So if we now do the equation of ammonia reacting with H+, what forms is ammonium. What we need to do now is show what's going on here. And so here's the picture. So the nitrogen, it's doing something rather funky. The nitrogen, with its lone pair of electrons, can pick up an empty H+ ion. We know that a hydrogen atom looks like this, with 1 electron. Yeah, it becomes a H+ ion by losing that 1 electron. Yeah, that 1 electron has been lost. So it's got no electrons in its outer shell at all. So what that now means is that we can now form a new bond. And we now see for the very first time our diagram of a dative. So what now happens, this is where I'm running out of space, I'll try and move everything over, is H+. Yeah, and what happens is that we form a 4th covalent bond. But this time it's dative, because instead of having the dot and cross, 1 electron coming from the inner bracket, there we go. And if you want a stick picture, it looks like this. We now pick up our dative bond there. Now, there's no difference in the strength, just to let you know, they are identical. In fact, you cannot tell the difference between a dative covalent bond and a standard covalent bond. So once it's actually formed, you couldn't tell which one was the dative. You wouldn't be able to actually know, because the strength of these bonds is exactly the same. But we represented in the diagram with an arrow for one of them. If you didn't want me to do that one, I could have just made any one of these the dative that I wanted. It makes absolutely no difference at this stage because they have the same strength as each other. Cool. So dative bonds are really straightforward, but the problem is then trying to recognize them. Before I do the recognition, I'm going to give you example number 2 from Edexcel. Example 2. Now this one is much more complicated, and this one comes from aluminium chloride. Now aluminium trichloride itself is an odd compound, because at IGCSE, you'd call that ionic, metal, non-metal. But we now realize at A level, it's not. It's actually covalent. By the way, if you really want me to write the word simple, I will. Yeah, this is actually truth. This is true. And they're probably going to ask you why, and you're going to say the fact that there's a big difference in electronegativity. Second point between, so if they ask you to explain this, explain. Yeah, first bullet point, big difference. Big diff in elecneg between Al and Cl. First bullet point, aluminium 3+, very high charge density. High charge density. Third mark, polarizes chloride ion, so becomes covalent. If you want the diagram to me to explain this, I don't deal with bullet points like that. I just have a picture in my head. The image we'd imagine GCSE is this one. This is GCSE. Yeah, but we know that's not true. Yeah, what we actually realize is this. This is IGCSE. Yeah, you'd actually put them all in brackets with all their dots and crosses all over the place. But whatever, I'm tempted to do that actually. Like, I can do that. Like, each of these is going to look like that, and I can do the same thing for the others. But in reality, it actually looks like this for A level. Yeah, for A level, what happens is because the aluminium is so tiny and highly charged, what happens is they become polarized to the point where they actually link together. Yeah, and have an electron density map where they overlap. Sorry about the poor diagram. There you go. The electron density map, by the way, for ionic. Yeah, so ionic electron density maps, you see atoms where they don't overlap, and then in for covalent, what happens is you get this. You get overlap of one of the shells. Yeah, this is ionic, a distinct gap between them, but then covalent now gains this overlapping shell where they link together. Yeah. Okay, so aluminium trichloride, there's no dative here. Let's just explain why at the minute there's no dative. The reason being is because aluminium had 3 electrons in its outer shell, and it's forming 3 standard covalent bonds. Looking like this. There we go. So it starts off absolutely as normal. Yeah. Now, something really cool happens. You get what's called dimerization. Oh yeah. Oh yeah. So subtitle is dimerization, when two molecules join together to form one larger molecule. That's the actual definition. I do like to add in nothing lost. They just link together. There's no other product from this. They just link together. Yeah? You can also have, by the way, trimerization. Trimerization, when three molecules link together. Yeah, join together to form one larger. And then you can also have, from GCSE, polymerization. Polymerization, where many molecules join together to make one larger molecule. So anyway, dimerization, I'm just going to get rid of those, don't do that. So I now need to explain to you what's happening with the dimerization of aluminium chloride, and here's what's happening. So I'm going to zoom in. Zoom. Okay. So aluminium chloride originally looked like this. Here's the stick picture. Let's convert that into dot and cross. Every atom gains a circle. 3 standard covalent bonds. Now, the reason why this is genuinely an interesting molecule is aluminium is in a very odd situation. Does anyone on the chat, please? Question: why is aluminium in an odd situation here? So what does dimerization look like? Two aluminium chlorides. 2 aluminium chlorides. Seeing how long it takes someone to post an answer on the chat. Come on, guys, you're better than that. Why is aluminium in an odd situation in aluminium trichloride? So dimerization, what's going to happen is these two molecules are going to join together, and there are no lone pairs of electrons. Well done, Aisha. Absolutely. It's not what I'm after, though, but I like it. It's a good answer. Don't mind it at all. Anything else? There's a better one. We know the main reason why atoms bond together is so that they become stable by filling their outermost energy level. Well, that ain't full. Aluminium's now only got 6 because it doesn't have a full shell. Thanks very much. So, very odd situation. So what can now happen is, because aluminium has an empty space, what can now happen is it can dimerize. They can link together. And the final picture looks like this. Aluminium, Cl, 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 aluminium, Cl, Cl. And what we realize is that we have that one, that one there going from the chlorine, and then this one, of course, also coming from the chlorine. Whereas these ones are standards. Really funky example. I mean, how cool's that? And that is pretty cool in my eyes. Dimerization. That's a normal, that's a normal, that's a normal. Lone pairs, lone pairs, lone pairs, lone pairs, lone pairs, lone. There we go. So the stick diagram of this looks like this. Normal, normal, normal. Dative, dative. Normal, normal, normal. How funky is that? Aluminium. That's the dimer of aluminium chloride. So that then becomes Al2Cl6. Isn't that funky? If anybody's wondering if this can continue, you can actually get, under very extreme conditions, you can actually form a giant polymer structure. But you don't have to cover that. So dimerization is lovely from the example of the dative covalent. They love this example, guys. It appears a lot in the exams. I don't know whether or not I've actually got one of these. I was trying to find edXL exam questions. So an aluminium chloride one. Oh God, I need to take that one as well. Blimey. Dot and crosses are now getting hard, and they do require a bit of teaching. I'm going to steal that. All of these are edXL. Steal you. Hello. Right, so we're done with dative covalent. I do want to show you that you do need to be able to identify it and recognize it. I want to show you an exam question of that type as well. So if I now Google, actually I might have one. Do I have one already? I might actually have one, because I was putting together a homework for you guys. I was putting together a homework, and I might actually have one of them. Let's see if I can find it. WIMPs. Is it going to be there? Please be there. Please be there. Please be there. It's not going to be there, is it? It's not going to be there. Oh, darn it, it's so close. I need to show you some of these questions. I'm actually going to go to, I know where these are on AQA, but I don't know where they are on the Edexcel ones. They are about. It's just going to be easier for me to find one on this, I think. Probably. Let's see if I can find one. An equation. Doesn't look like there's one on that one. Let's try 15s. Oh. No. As I said, this is just because I happen to know these papers better. Shapes should be anywhere around here. But they are worth showing because students find them really hard. Solubility, is it going to be next? No, I took that one. Oh, no. Okay, not that one. Let's try the 14 paper. I just need to find one to show you what they're doing. Oh, type of bond. Oh, type of crystal. Come on, give me what I'm after. You mean things. It might be on the new ones, darn it. Come on. Come on, be nice to me. Wow, they're really frequent. I'm surprised I can't find it. Let's do 12. God, that's going back a long time, although I am pretty old these days. I do need to find one of these. They're like super frequent. I can't believe I haven't found one. Maybe they're on the new papers. Come on. The problem is I'm skipping really quick here. Ah, there. There it is. So, state the type of bond that's formed between phosphine and H+ ions. So that's going to be a dative. And I know that's going to be a dative because H+ has no electrons to give. So it must be a dative. Predict the bond angle. We'll do that next time. Let's go for the next one. I just want to show you that this is really common. This comes up a lot, man, and I'm sorry that it's taken me so long to find them. As I said, there is a very high likelihood that I've just skipped past it. I'm glad I found one. I want to find one where it's just a normal covalent. All these, there it is. There. Check that one out. That one's a great example. Right, so I'll take that one. This is a nice question. So now, first of all, the first thing I kind of want to mention here is students often go, how am I meant to know if it's a dative covalent or not? Well, it's actually a tricky question because that's actually really complicated. But in reality, this question screams dative covalent. Like, there are ones of these, by the way, where they're just normal covalent bonds. But what I would actually do is draw out these two into pictures to see what it looks like. So this one is going to be nitrogen at the center, and then H, F, and F. And we know nitrogen has a lone pair. It's probably going to be dative now. And that nitrogen's now joining to boron. It's going to be dative. Yeah, and then the boron also has 3. Yeah, so it had a slot as well. So that it's going to be that way. It is going to be dative. I know this is tricky, guys. I do. These are not easy questions. And then when it says explain how this bond is formed, both electrons in the bond came from the nitrogen. Yeah, this takes practice, and you've got to do that in under 2 minutes. This is not easy, folks. These take practice, these questions, and I need you to be working on them. So trying to spot that. I'm wondering on that paper, I remember this paper, whether or not it has immediately afterwards one that's not dative. No, it doesn't. And it drops into a different bonding type. Let's irritate. Ionic bonding comparison. Anyway, so nice to see what it's doing, yeah, in terms of trying to identify these. They do take practice, and they're not easy. Okay, so I can tick off coordinate bonding. Now, at this point, we now drop into dative covalent. Sorry, we're done with dative covalent. We're dropping into dot and cross. Now, you guys have been doing dot and cross diagrams since GCSE, and I think everyone tended to find that these were just relatively easy things to do. They're like, oh, yeah, you just draw the circles. You take the sticks, you draw circles around them. Yeah, so we can now do a subheading of dot and cross. Dot and cross. And the way I teach this at GCSE, so for example, if you were given methane and asked to draw the dot and cross, the first thing you do is convert it to a stick diagram, knowing your bond rules. You know that carbon makes 4 bonds, and hydrogen always makes 1 bond. So you can convert it into a stick picture. Then what you do is you draw circles around each of them, and where the sticks are, you show the overlap. Yeah, like this. And then you just put a dot and cross in each one. Yeah, and then you add on any lone pairs that you need to. Hydrogen doesn't need it, so the picture's done. But then you get trickier ones at GCSE, like CO2. Convert to stick. Carbon. Right, carbon makes 4 bonds. We know this. Carbon makes 4 bonds, and oxygen makes 2 bonds. So then you get, oh, so I'm going to have this picture. So then what you do is draw your circles around each one of them, show the overlap, and then in the gap, because there are 2 sticks, there are 2 sets of 2 pairs, a dot cross and a dot cross, and then a dot cross and a dot cross, representing the 2 sticks. And then you make everybody add up to 8. So in this case, carbon's already happy, and then you've just got to add on the extra electrons for oxygen, and we're done. Yeah, everyone now adds up to 8. So that was a trickier example then from GCSE. You can then go to another tricky example from GCSE, something like nitrogen. Yeah, convert to sticks. We know that nitrogen makes 3 bonds, so that becomes N1, 2, 3, N, and then draw the circles around each atom, and then in the gap there are 3 bonds. So I'm now going to go 1, and then 2, and then 3. Yeah, and then make everybody add up to 8. Yeah, and you're done. Not complicated. You know, these take practice to do this even at GCSE. They're not the easiest of questions, but you know, you kind of get to grips with them. Now everything changes. The whole thing gets really hard. So let's show you how much this changes. So in A-level, all of a sudden, so I've just gone to A-level papers and grabbed as many examples as I can. So it says here, draw the dot and cross diagram for sulfur dichloride. Right, so convert to stick. So it's telling you the number of chlorines that sulfur is attached to. If that had said sulfur trichloride, you'd have added 3 Cls onto it, but they've given you this one. So what we now need to do is convert it to a dot cross. And this one's a nice, easy one. This is GCSE, really. So we put in, there's a single bond between each one of them, and I now need to make everyone add up to 8. They don't really care in terms of, as long as in the gaps they're all correct. I'm just going to put the sulfur as X's and the chlorines as circles. Makes no difference, really. But that's a nice GCSE one, a nice easy AS one. Yep. Now look what they do. Sketch an electron density map. Oh, okay. So how many shells does sulfur have? Sulfur has 3 shells. So then chlorine also has 3 shells, yeah, on either side. And then what I'm going to do is just draw them all overlapping like this. There we go, electron density map. Next, oh my God, look at this. So it says iodine pentoxide. Each iodine is bonded to 3 oxygen atoms, and one of these oxygen atoms is bonded to both iodine atoms shown in the layout. Draw the dot and cross. Now that is hard. So the first thing to realize is that everybody doesn't have to add up to 8 now. Everything changes. And what you need to work out is the number of bonds everyone is making. Now we know that oxygen is always 2-. Yeah, what that means is it's usually making 2 bonds. Yeah, if oxygen is in a 2- state, it is making 2 bonds, unless there's a charge. Come to that in a minute. But there's no charges anywhere on here, so 2 bonds must be formed. But what's the charge on the iodide? So now we need to work it out. So we have got I2O5. Question, guys, what is the oxidation state? Oxidation state of I. Go. On the chat, please. See how long it takes you guys to do it. The oxidation state is going to tell you the number of bonds it's making unless there's a charge. And as I said, we'll come to that. Louis says +5. So we've got -2 times by 5, which is -10. 10 minus. Therefore, it must be 10 plus because there's no overall charge. Divided by 2 gives me 5 plus. Well done, Louis. Oh, Harry. Remember, you can't get above +7. It's a rule in chemistry. If you write down +10, you know you're wrong. Right, so that's telling me that iodine is making 5 bonds. 5 bonds! Right. So how is this possible? Let's link them all together. Atom, 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 atom. Each iodine is making 5 bonds. How could we get 5 bonds out of this? Right, so 5 bonds. 1, 2, 3, 4, 5. That seems reasonable. Would you agree? Each oxygen is making 2, and each iodine is making 5. Winner! Right. So now what we can do is we can do this. So we can now just fill in the gaps. 1, 2, no datives either. Each oxygen is making 2. Make everyone add up, make all the oxygens add up to 8. Oxygen always has 8. There we go, and I'm done. See, it's really quick when you know what you're doing, but these are all, every single one of them just requires a little bit of thought to it. And yes, the iodines in the center have now got 10 electrons in their outer shell. What that means is they're in a funny hybridized state where the subshells are blended together to allow them to make more bonds. Next, right, let's have a look at this one. Potassium, right, now we've got a charge. Right, there's a charge issue. What that means is, if there's a charge, it means that somebody in this, and it's going to be an oxygen, one of the oxygens is going to be fully negative. Well, that means it's only going to make 1 bond. It's got to actually have stolen an electron from someone. I'll do it. So first thing we need to do, ClO-. Right, guys, what's the oxidation state of chlorine, please? Off you go. Oh, sorry, ClO4 1-. Go. What's the oxidation state of chlorine? Louis. Sorry, add the 4 on. My bad. My bad. I want a piece of ginger. Stick my finger in the tea. Thanks, Louis. Better. Right. So how many bonds is it making? Seven. Yeah. Right. It's +7. It's making 7 bonds. 7 bonds. 7. Ah, him. He's got to be minus. Right. Add on the electrons. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, and there's the extra. Yeah, that's why it's fully minus. Got to be careful to get oxygens, not to add too many electrons. It's easy to do that. There we go. We're done. And there, that electron there is what makes it negative, and they got that from the potassium. Yes? Looks like after a while you kind of go, hang on a sec, that's actually not a bad method. It kind of works. Like, I've seen students spend 10 minutes on these stupid diagrams and still not getting, they're just making stuff up. And you can't, you just need to learn this process. Right, next one, hydrogen chlorate. Okay, so the amazing thing about this is we've got hydrogen as a +1. We've got chlorine as a -1. Oh no, hang on a sec. That's interesting, isn't it? We've got oxygen at -2, and chlorine is in a +1. Ah, chlorine's making 1 bond. Just the 1. Oxygen's making 2 as normal. Chlorine's making 1. Put on my numbers. Put on my 1 bond. Whatever, we're done. Finished. It's an easy one. just GCSE, really. Right, let's find another one. Guys, have a go at this one. Note the charge, please. Everyone now have a go at this one. So the ion is Cr2O72 minus. Off you go. Try and draw a dot and cross for that guy. And then have a go. Pause the video. Pause the video. Oh, wow, actually, just delicious. So many emails today. Just gotta forward an email. Right, you all ready? So first thing I'm going to do is, how many bonds is chromium making? So we've got -2 times 7, that's -14. And then that one there, oh, -2, so that must be bringing +12, but there's 2 of them in it, divided by 2 plus 6. I shouldn't do that, it should be the other way around. 12 divided by 2 plus 6. Each chromium is making 6 covalent bonds. Right, 6. Right, and 2 oxygens with charges are going to be there. So they're going to have the lone pair, they're going to have that extra electron. Right, let's now turn these into circles. Really hard picture. They didn't even make it easy for the real. Lots of students didn't even realize the link between the 2 of them. It's a bit of a nightmare. Oh, it was messy. It's messy. Ugh. It's horrible. Right, dots and crosses. 1 bond, 2 bonds, 2 bonds, 1 bond, 1 bond. 1 bond, 2 bonds, 2 bonds. Right, that one now has an extra electron minus, extra electron minus. No, too many, no, that's correct, we get to 8. And then, oh, picture. That one's also got the lone pairs on as well. They won't care about how wonky-donkey the oxygen dusters are, as long as they all fit in. There we go. Not an easy exercise. We can have a go at some others as well, whilst we're here. So tick it if you got it right, folks. Let's have a go at the next one. How about this one? The nitrate ion. What about that? Draw that ion. Oxidation state of the nitrogen, -2, times by 3, -6. It's making 5 bonds. Nitrogen. Oxygen, oxygen, oxygen. 5 bonds. Nice. And that's got the charge. There's the extra electron. Doesn't need that one. 2 bond pairs. I'm going to color code that. Yeah, the 1 bond there, then 2 bonds there. 2 pairs there, and then 2 pairs there, and then make everyone add up to 8 except for nitrogen. Yeah, and then that one all adds up. And that one's got the extra electron. That's denoting the charge. Does that make sense? You ready for the next one? See, you can do these all day. SO42 minus. What about that one? Work out the charge. O2 minus times by 4. 8 minus. -2. It's in +6. Sulfur's making 6 bonds. Sulfur. Oxygen, 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 oxygen. How do I get 6 out of this? 2, 2, 1, 1. Fine. He's got the extra charge. He's got the extra charge. 1 minus, I meant 2 minus SO42 minus. Draw on all your electrons. Electrons There you go, 2 pairs in that one, 2 pairs in that one, 1 pair in that one. Make everyone add up to 8. Careful not to add too many to the ones with the double bonds. Oh, and oh, we're done. Yeah. Do I do another one? See, it's an easy game once you get used to this. It's just a game. Find the oxidation state, work out the number of bonds, distribute them evenly. Yeah. Let's do a carbonate. Why not? CO3 2-. Oxidation state of carbon. So we've got -2, 3 -6, 2 +4. It's making 4 bonds. Four bonds. 1, 2, 3, 4. Ah, there's the minus. He's going to have an extra. There's a minus. He's going to have an extra. Make everyone add up to 8. 1 bond. 1 bond. Add up to 8. 2 bonds. Add up to 8. And then oxygen. And I'm finished. Thank you. Carbon's making a standard number of bonds. So there is a trick to this. This is a game, and you've got to learn to play it. So at this point, draw down cross and use oxidation states. I'm done. I'll set you the homework for as many of these as I can find. They're all over at Excel papers. As you can clearly see, they've been everywhere. And I'll find a dimerization one as well. But that actually brings me to the end of my lesson. Right, doing really well. Back to that. Right, guys, so end of the lesson. We're nearly there now. I've got 2 more lessons on shapes, and I'm done. So, and then you're going to have a mammoth test. So, guys, I'll see you next lesson. Hopefully see you tomorrow. Have a great rest of your day. Enjoy your lunch.